So we're going to skip up to section 5.6 and keep all of the polynomial sections together because it just makes more sense to us as instructors. So in section 5.6, we're going to talk about the real zeros of polynomial functions. So up to this point, we've been using a factored form of a polynomial to graph, or we've been factoring it in order to graph it. Well, what happens if it's not factorable by previous methods or means? So 5.6 and 5.7 are all about what do you do when it doesn't factor. So what we already know is this. So we already know how to find, sorry, I set the marker down and lost it. The real zeros of a quadratic function, which is a polynomial. So if I gave you f of x is equal to x squared plus x minus 6 and asked you to find the real zeros. Now remember, the real zeros are the same thing as the solution. If we set the function equal to 0, it's also the x-intercepts, which we really used in the last section. So what I'm asking you is if you said x squared plus x minus 6 equal to 0 and found the real solution, the real zeros, could you do it? Yeah. The technique you would use would be factoring, which would be quickest. You could also use the quadratic formula, but only because it's a quadratic. So we'll say or the quadratic formula QF. Factoring is always quickest though, just as a reminder. So to do that, we come in and just factor this as x plus 3 and x minus 2 equal to 0. So x is equal to negative 3 would be 1, 0, and x equals to 2 is another 0. Now the real zeros are the ones that we're going to be able to graph on the number line. So keep that in mind that these are the ones that do not involve complex numbers or i's. So, okay, but what happens if the polynomial is not factorable? So what you see on your handout there is a polynomial function that is not factorable. So something like f of x equals x to the third plus 8x squared plus 11x minus 12. So this has 4 terms. If you could try and use grouping, you pull something out of the first half, which would be an x squared. That leaves you with an x plus 8. There's nothing in common over here, and you won't be left with an x plus 8. So it doesn't factor by grouping. So we need some other methods. So this particular section has a lot of theorems in it, quite a few of them. You're not necessarily responsible for knowing their names, but you are responsible for knowing how to use them. So we're going to walk through each of them and show you how to use each one of those theorems. Then when you do the homework and it says use the remainder theorem, you'll know what we're talking about. So the first theorem is yes, indeed, the remainder theorem. And it simply says you have a polynomial function f. If f of x is divided by a factor of x minus c, then the remainder is f of c, which makes sense. If you do a division process, then you get a remainder. But this particular remainder could be found by finding f of c. So example 1 talks about this particular one. We're going to use the same polynomial that's already on the board, and we're going to divide that. So we're going to divide by this nice linear factor of x minus 1. So I could come in and do the long division. The long division would be putting x minus 1 out here. You put the x cubed plus 8x squared plus 11x minus 20 on the inside, and you do the long division. However, we can actually come in and instead of using long division, evaluate the polynomial at 1. And this is what the remainder theorem says. Where did the 1 come from? Well, if you took x minus 1 and set it equal to 0 and solve that, you'd see if 0 is positive 1. So we're going to try 1. And what we're going to do is put 1 in. So we'd have 1, we'll cube it. We'll take 8 times 1 squared plus 11 times 1 minus 20. So that would be 1 plus 8 plus 11 minus 20. That's 9. That's 20 minus 20. Sure enough, I get 0. So what we're saying is that this 0 is the same thing you would get if you did this division process. You'd have a remainder of 0. So this was much easier than that, no doubt about it. Okay, let's do the same polynomial. This is part B on that same problem. They want us to divide the polynomial by, this time, x plus 3. So we divide by x plus 3. So we're going to find f of negative 3. So that would be negative 3 cubed plus 8 times negative 3 squared plus 11 times negative 3 minus the 20. That's going to give me what? 27 negative. Negative 3 squared is a positive 9 times 8 is 72 minus 33 minus 20. And if you run that through, you'll get a negative 8. So what they're saying is that the remainder, if we were to divide this by x plus 3, the remainder over here would be that answer of negative 8. So if we divided this by x plus 3, we get a negative 8. Well, that's interesting, but what does that have to do with finding these zeros, right? So it's interesting, but how does it help us? So that leads us to our next theorem, which is called the factor theorem. It says let f be a polynomial function again, then x minus c, so x minus 1 or x plus 3, is a factor of the polynomial function if and only if, when you evaluate it at that c value, you get a 0. What does that mean? Well, it means a couple of things. What that means is in this previous example, that x minus 1 is a factor of this polynomial because the remainder was 0. So in other words, I could take that polynomial and I could factor it into x minus 1 times a whole bunch of other stuff, right? Because the remainder is 0. I could not factor it into an x plus 3 times other stuff because the remainder was not 0. So it consists of two separate statements. One statement is that f of c is equal to 0, then x minus c is a factor. So f of 1 was 0, so x minus 1 is a factor. And if x minus 1 is a factor, then the remainder had better be 0. So it's a two-way street. So that leads us to our next example. So example 2 says, let's use the factor theorem to determine whether or not x minus 2 is a factor of f of x equal, we're dealing with a different polynomial this time, 4x to the 4th minus 15x squared minus 4. So I want to know whether or not this is a factor of that. And again, it may not be factorable, but we have a mechanism now of saying whether or not it is a factor, which is great. So the first method is what we were just doing. We're going to evaluate the function. We're going to find f of 2. So this is method 1. We'll just do f of 2 using functional notation. So that would be 4 times 2 to the 4th minus 15 times 2 squared minus 4. So 2 to the 4th is 16 times 4 is 64. 2 squared is 4 times 15 is 60 minus 4, and sure enough, we get 0. So the answer is yes. X minus 2 is a factor. And I know it's a factor because the result is 0. And that's what the factor theorem is telling us, combined with the remainder theorem. Okay, that's one method. There's nothing really wrong with that. It does work. But there's actually a quicker way and a more efficient route to our final answer. So method 2 is asking us to come in and use the remainder theorem with synthetic division. So instead of plugging it in, we are going to do a type of division, but it's synthetic division. So this is method 2. So method 2, to do synthetic division, and if you've never done it, it's very easy to pick up, but you do have to practice it to get better at it. So we're going to put what we would be dividing by over here in a box. Again, I'm going to switch its sign, just like we're finding a 0 or evaluating it, I switch its sign. What we now need are the coefficients of what we're trying to divide into. So instead of writing out the whole polynomial, we're just going to nab those two coefficients. So 4, that's the x to the 4th power. I'm going to recognize that there is no x cubed term, so I'm going to put a 0 as a placeholder. I do have an x squared term, so I'm going to use the negative 15. And then I also have, oops, I don't have an x term, so I'm going to put a 0 there. And then I have a constant, so this is the constant. So I have these zeros that are sitting in there for the missing terms, and they are really, really important. When you think about doing long division and decimal places and place value is important. So same thing here. So to do the actual synthetic division, you're going to bring the first number straight down. That's the 4. You're then going to multiply the number that's below the bar, the 4, times the number in the box. So 4 times 2 is 8. That goes in the next column. And then we'll add that column. And then we're just going to repeat that. So we multiply 2 times 8, which is 16. Then we're going to add that column, which is 1. Multiplying 1 times 2, which is 2. Adding that column gives me 2. Multiplying 2 times 2, which is 4. Adding that column is 0. And that's the same 0 we would have gotten when we plugged the 2 into the function. So that over here is the remainder. And because it's 0, we know it's a factor. No. X plus 2 is a factor. Great, wonderful. So I don't know, that might be a little easier. Let's walk through it really quickly one more time to make sure you've got the process down. Always bring the first number straight down. Then you're going to multiply. So 4 times 2 gives you 8. Goes in the next column, add that column. 2 times 8 is 16. Adding that column. 1 times 2 is 2. Add that column. 2 times 2 gives us positive 4. Adding that column gives me 0. Why do we want this? Well, because what we really are doing is we're breaking apart this polynomial function. So right now, we know that this 4x to the fourth minus 15x squared minus 4 factors into that x minus 2 that we just found as a factor. But what is this 4, 8, 1, and 2? Well, we took this x to the fourth, we divided it by an x, so this guy is really belonging to the coefficient on an x cubed term. This 8 belongs to the x squared term. We're just going to count down. This 1 belongs to an x, and then we have a positive 2 sitting there. So we now know that this polynomial function factors into x minus 2 times, and I won't get this in here, 4x cubed plus 8x squared plus 1x plus 2. So the synthetic division process was really powerful because it gave us the fact that it was a factor, but it also gave me, if I were to factor this out, what we are left with as a depressed equation. So this guy is called a depressed equation, and it's called that because you depressed or lowered the exponent, the degree, by 1. So it got depressed down to a cubic. We started off with a 4th degree, now we have a 3rd degree. And that's what the synthetic division and the remainder theorem combined with the factor theorem all tell us.